In a database, the basic storage unit that we call it as a table or tables. All the tables inside the database makes the one big database. A database, if you look at the smallest storage unit, that comes to tables only. And this is also an interview question. What are all the objects in the database that actually takes the space? So tables are one of those objects which actually takes the disk space inside the database. And also, apart from tables, the indexes that you create or the indexes that Oracle creates for you, those are all also takes the space on disk. So basically only two objects inside the entire database takes the disk space. It is the tables and it is the index. In this lesson we will understand about the tables and the table clusters. Table clusters are nothing but a big table which has multiple tables inside it. That is nothing but called as table clusters. Let us start. First of all, we'll need to understand what is the difference between a database user and a database schema. See, let us understand an example. When you go to a supermarket, now when you go to the billing counter, the person who's doing billing for you, he is also a user because he is using the application or the system to generate the bill. And if you go to the self-billing counter, the customer becomes the user. And let's take when you call the call center of the supermarket, and let's take you have an issue in the bill. So the person who is playing around with your bill by adjusting the items, now he also becomes a user. In real time, there are multiple users for any application, but inside the database, a user will never map to a real-time person. You cannot have a user is equal to customer or user is equal to the biller or user is equal to the owner of the business. In database or inside database, a user maps to an application user. Now that application can be used by a number of people. That's irrespective. That can be again the customer itself or the biller or the call center person who's helping you, because all of them will use an application that speaks with the database. Now that application will have only one user. That user will be in common, used by all of them. Remember, always inside the database when you create a user, it must be an application user. It should not map to any real-time user. For example, you shouldn't have a username called as customer, or you shouldn't have a username called as product. Rather, you should have very logical usernames. SAP HR, for example, is one of the user ID for SAP databases, which will show or which will depict that, okay, SAP HR or an HR person or HR module of SAP is being handled by SAP HR user. And likewise SAP Finance or SAP Fin, that can be a user which is created to handle the SAP Finance application. And let's take SAP Log, that will be a user which will be handling the logs of the entire SAP application. That's how all the users inside the database must be created based on the application roles, not based on the real-time users. And database schema. Once you create a user inside a database, it doesn't mean that you can call it as a schema. There is a very small difference between database user and database schema, and the difference is when you create a user inside the database, let's take we create a user called as SAP HR by issuing the command create user statement. It simply means that a user has been created and the user has the permission if you give. So I'm using this word, if you give some permissions to the user, then the user can access the data from other available objects or available objects of other owners inside the database. That is only a creation of a user. Next, when the user becomes a schema, if you create some objects with that user inside the database, then you call it as a schema. So any user, if it's owning any single object inside a database, it simply becomes a schema. The user must be owner of the object. It doesn't mean that user is having access to other objects. It doesn't become a schema. It must own the object. And how would a user own an object inside database? When the user logged into database and creates database object by itself. And that's when user turns to a schema. Now database users are different from OS users. Simple as that. When you connect to a database, the database user is totally different when you compare with the OS level users. For example, in general, if you go to any environment of the Oracle database environment, real-time environment, you will find that database user name is totally different when compared to the Linux OS username. So in most of the environment, you have Oracle as the user who owns the database installation, but inside the database, as I told, we can have SAP HR or SAP Fin or SAP Log kind of users. Of course, sys is the super user. So in general, you log into Linux machine via PuTTY, and once you log into PuTTY, you will connect to that machine as Oracle user, because Oracle is the one which owns the installation, and from that you connect to the database as sysdba. That is how generally DBAs work in real time. And DB user and OS user can be same. You can have Oracle as the OS user, or you can have Oracle user inside the Oracle database also. Of course, that depends on the requirement, but as I told you, no, the database user will never map to a real-time user. Now OS user becomes a real-time user. Database user must always be the application user. Next, user are created by create user statement. Now this is what happens inside database. A user is created when you issue the create user statement. Next, schema is a user in database who owns at least one object. Now when do we call a user converted to schema? When the user owns at least one single object inside database. Now each user owns a single schema. Remember, every user can own only one single schema, and both schema name is exactly same as the username. For example, we have HR user. How HR user will be created? By issuing a create statement. Create user HR identified by XYZ. Now you have got the HR user created. Now let's take the HR user, you connect to the database, and then you create a table with HR user. It becomes HR schema. HR user will be mapped to only one schema, and the schema name will also be exactly same as the username. You cannot have multiple schemas which are assigned to the username. It is one-to-one mapping. You have one user, you have one schema. The schema name is always same as the username. That is how the database works. Next, DB user has password and privileges. Remember, the password and privileges are given to DB user, and of course that again drills down to password and privileges to schema. In production, schema owner represents a database application rather than a person. Schema objects. Next is, what are the schema objects that a user or a schema can hold or can own? Remember, schema and user, these two terms will be used vice versa because they are very close, or there is a little difference between both of them. So going forward, if I refer it as a schema or a user, understand that both of them are one and the same. Schema objects are nothing but the user objects. So these are the objects that can be owned or have access to the user. So each object has a unique name referred as schema name dot object name. Actually, this is the correct way to access any objects inside database. Of course, most of the users will directly query the object name, but you can query the object name until you are the owner. For example, select star from EMP. If I give this statement while connected as HR user, it won't work because HR user does not own the employee table. That's the reason the correct way to access any object inside the database is the owner of that object and the object name. Also remember, let us assume you have employee table both in Scott schema and you have the employee table in HR schema. We can very well have these tables. When you specify Scott.employee table or EMP table, it will query the employee table of the Scott user. And when I query select star from EMP, this will give me the results from the same HR schema, because HR schema also owns an employee table. So you need to be always specific about which object you are querying. It's a very good practice to use the schema name dot the object name. Also, while connected to the user or the schema name, you can even give the same schema name HR.employee when you want to be specific like which object you are querying. Next, HR.employee refers to employee table owned by HR schema. This is an example. When we write HR.employee, it simply refers to the employee table which is owned by the HR schema. Let's take there is another schema inside the database where we have the employee table. To refer to that employee table, you need to give schema name. Let's take Scott.employee table. But remember, HR schema must have the at least select permissions on the other schema table. Then only it will be able to query the other table. For example, let's take HR schema wants to query Scott.emp table. Then HR must be granted the select permissions on select.employee table. So how do you give? While connected as sys user, you need to issue the command grant select on scott.emp to HR. This is a command to grant select on scott.emp table to HR schema. Remember, this will only allow HR user to select the data out of the table, but it won't be able to update, delete, or perform any other operations. But in case if you want to give entire permission, like how the owner can play around with the object, if you want to give those permissions, then grant all on scott.emp to HR. What HR will do? Now HR has all the permissions to insert, update, delete, alter, and play around with the employee table as the owner has the permissions. Once you give the permissions, once you grant the permissions to the HR, then HR can query the Scott.employee table while connected as HR user. Next, schema owns different types of database objects like tables, indexes, partitions, views, sequences, etc. There are many database objects. These are only few of them. We have triggers, functions, cursors, and many more. When you get into PLSQL, again, you will have some more packages. Triggers and functions are all part of the PLSQL, but also those all are considered as database objects. All schema objects are stored in data files. There's no doubt everything is stored in data files. Okay, so DB is running, switch user Oracle. Fine, so how do we check the tables inside the database? As sys user, you have DB underscore tables, describe DB underscore tables. So this view will have the details about all the tables inside the database. It's nothing but the metadata about all the tables. But apart from tables, there might be other objects that are owned by different users. So the best view to check all the objects would be db underscore objects. This one will have all the objects, not only the tables, but apart from tables, views, and all the objects inside the database. So this view will have everything. And this one, we can query that. Select, I just want to see who's the owner of employee table and do we have multiple employee tables inside the database with the name EMP. So select owner, object name, and object type from db underscore objects, where owner, or we'll say object underscore name, is equal to emp. It's saying the owner is Scott, emp is an object inside the database, and this object type is a table. This is how you can query the db underscore objects to get the details about a particular object. And also the same information would be available in db underscore tables. Let us query db underscore tables to get the details about the table and the owner. We have owner, comma table underscore name, comma table space underscore name from db underscore tables, where we'll say table underscore name is equal to emp. It says that it's owned by Scott user, table name is emp, and it resides under user schema. This is how you can play around with the metadata to get further details about a single object. Next is tables in database. As we know that table is the building bond of the database or building structures of the database, and this is the only object apart from indexes which takes the physical disk space. Let us understand about tables. It's the basic unit of data storage in the form of rows and columns. Your table will store the data in the forms of rows and columns, and you have multiple columns where you have multiple rows inside it. And also sometimes columns are also called as attributes and rows are also called as tuples. Tables are permanent or temporary. Now there are two types of tables inside the database. Some are permanent table and some are temporary tables. Now the question would be, what are those temporary tables? When you perform sorting in your query, or when database wants to perform some kind of sorting inside the database to get the results, at that point of time, what Oracle will do inside the temporary table space, it will create some temporary tables where it can perform the sorting. Now those are called as temporary tables because they can be flushed out and they can be overwritten or played around by Oracle itself. That's why inside the temporary table space or the temp table space, nothing will be permanent. Once you shut down the database, everything will be flushed out, and once you start the database, you have a clean temporary table space. It can be considered as RAM because in RAM also we have all the contents, but once you shut down and start the system, there won't be anything in the RAM. That's how temporary table space, of course it resides on hard disk, but it acts or works like RAM. Now table columns consist of data and have specific data type. To distinguish the data inside a table, every column is assigned with the data type. It will help Oracle understand what kind of data or what nature of data is coming inside a column. For example, the name column will have the character data type, which means inside the name there won't be any value which is related to date or numbers. It will help Oracle understand, okay, everything inside the name column would be some characters or alphabetical characters. Same thing goes with the date column, where Oracle understands that, okay, every data which will be coming inside the date column would be related to date. You won't have characters or alphabets into it or some kind of uh, the words or real-time words coming inside the data column. Same thing goes with number column or timestamp column. We have different types of data types when it comes to tables or when it comes to columns. Next, each table is added with row ID column. When you create a table inside the database, row ID column will be created and it's a hidden column. Of course, you can query row ID column also, but it's hidden in general. When you perform select star from employee or any other table, the row ID column won't be shown. But if you add the row ID column, of course it will come. What row ID will do is it will have the physical address of each row. Physical address means where exactly the row is stored, so that next time when you query, if that row needs to be picked up, it will be picked up using the row ID. Now this all maps to what we have seen inside the logical structures. The row ID, it will be there in the header of the row ID. Then the same row ID will be placed inside the block header, because every block will have list of all the row IDs inside it. Then block IDs will be stored in the extents, extent IDs will be stored in segments, and then segment details are stored in table space. That's how the entire management happens inside the database. So row ID is used in indexes to refer rows physically. When you query any table or any data inside the table, what happens is first Oracle will check if there is an index on any of the columns, and if the index column is included inside your query, then it will use the index, directly pick up the row IDs from the index and throw the output. That's how it becomes easy for Oracle to navigate fast, and it also makes sure that database is not going into full table scan, like scanning all the rows inside the table. So rather than finding all the rows inside the table, it can directly pick up the rows which are requested directly because you have an index. So more about indexes and performance tuning we'll be looking at when we are in the performance tuning topic. So for now, just understand row ID column is used by indexes in order to pick up the rows faster from the disk. You can give partial or full privileges on tables to other users inside the database. Of course, we have different tables inside database, and in case if you want to grant some permissions to others, you can give the select, delete, update, or maybe all permissions to other users inside database depending on the application requirement. Now first of all, we'll understand or look at the row ID column inside a table, where it is. So let us will just check which user am I connected to the database. So show user, I'm connected to the DB as sys user. So I'll issue the command select star from EMP. What it says, table or view does not exist. What this command means is select star from sys.emp. But sys user doesn't own any employee table, and that's the reason there is no output. If I want to see the details of the employee table, I need to query it select star from scott.emp, because Scott user owns the employee table. I will adjust the line size. I will make it to 500 so that our output comes in one line. Great. That's the output from the Scott table. Employee table owned by the Scott user. Now let us try to check the row ID column. Select row ID, comma, EMP number, comma, ename from scott.emp. We can see that there is a unique row ID assigned to every row inside the employee table, which is owned by the Scott user. It's with every table. These row IDs are nothing but the physical address of the rows. When we create indexes on these rows, index will refer to these row IDs, and that's how index will pick up the rows directly from the physical address, and it makes the job pretty fast. For example, let's take there is no row ID column. Let us assume this column is not placed by default by Oracle. What will happen? When you query the table where you want to uh, have the output or the example or the output of the query would be this last record, which is like Miller, that's the employee name. When your query, we are expecting that the output would be this last row. For Oracle to come up or bring out this last employee record, it has to first scan through all the records that are available inside this table. It will go and check the first one. It will check if the employee name is Miller, no. Go to the next record, if the employee name is Miller, no. Go to the next record, employee name Miller, no. And that's how it will drill down to the last record. Now that is called as full table scan, where Oracle is scanning through all the records of the tables. But that's not the way, right? That's why the indexes comes into picture and the row ID will come into picture. Through indexes, what will it will do is it will match the Miller as the employee name inside the index. Now in the index you will have all the names that are starting with first M, so it will directly jump onto the area where the name of the employee is starting with M. So when we check the entire table where employee name is starting with M, how many records do we have? We have one Miller and we have Martin. There are only two records that start with M. And the next one would be, it will check in these two records how many records have the second alphabet as I, because we are searching for Miller, right? So only one record has the uh, alphabet at the second position as I. So simply what Oracle will do, okay, it found that one record which is satisfying the minimum condition MI is matching, and there is only one record available in the database, and then it will check for LLER. If everything matches, right away it will take this row ID and give the output. This is how the entire table scans are skipped, and that's how Oracle will give the output pretty fast. Now understand, this is a very small table where we have only 14 rows, and what if we have very big tables with millions of rows? If you don't have row ID and index concept, it will take ages to give you the output. Next is table clusters. What is a table cluster? Let us understand about table clusters in a more detailed way. We have different tables inside a database. When we query the tables, the data comes out of single table or maybe multiple tables depending on the query, if it is performing any join onto the tables. But remember, what happens when a query is trying to perform a join on multiple tables? There is no limit on the number of tables that a user can join, or maybe application query may join. Sometimes it might join all the tables inside a schema, or maybe some set of tables inside the schema, depending on the results the query needs. But inside Oracle, how Oracle joins the tables inside the databases, it will use the temp table space or the temporary area. Inside the temp table space, it will get the data of the first table, and it will have the data of the second table, this one. Next, the columns are picked up depending on the conditions. If they are matching any conditions, or if there are no conditions, then definitely all the rows will be matched up from both the tables, and the resulted rows will be given to the user output. This is how generally the queries or the join queries work inside the Oracle database. But what if a user is querying the data from multiple tables every time, or every time a user is sending a query, it has some or the other join inside it? What can we do to improve the performance? Or is there a solution to improve the performance of the multiple tables output? So Oracle came up with a concept called as clusters. Why can't we create a big table out of two tables, so that whenever the join query will come, it will improve the performance in terms of querying multiple tables? So let us look at how clusters will work in real time, or what is a database cluster. In simple, we have an employee table, EMP. We have a department table. Now both these tables will reside physically on disk, and definitely they will reside in separate areas. On physical disk, employee table might reside somewhere else, or it might even reside on a different table space depending on the owner where the objects are placed. Let's take employee table is in users table space, and department table space is somewhere in example, or maybe some other table space. Understand, when a user is querying the data from both employee table and department table, there is a join query. Then what will happen is, we'll also consider a join query. So how a join query will look like, this is a simple join, and there might be a lot of complex joins that might come inside the database. So select employee number, comma, employee name from employee, employee table. This should be EMP, where department number is equal to, now I'll create a join, select department number from department table, where department underscore name is equal to LOC, some location. How this query will be resolved? First of all, always remember the nested query will be resolved. So first Oracle will try to get the result of this select statement. It will go to the department table. It will get the department number from the table where the department name is LOC. Let's take the output of this query is the department number 10. So the result of this query is 10. The main query then shortens to select employee number, employee name from EMP where department number is equal to 10. First of all, the child query is solved and then it comes to the parent query. Likewise, if you have even multiple joins or hundreds of joins, that is how Oracle will try to solve all the joins. Next, what Oracle will do, it will go to the employee table and it will pick up the employee number and employee name where the department number is 10. So all the records are picked up from the employee table where department number is 10, and that's how the result is given to the user. Now when we drill down to the disk level querying or disk level data check, what will happen for the first child query, the department table, the example table space is queried or the data is picked up from the example table space. Now example table space on disk might reside onto a separate disk, or it might have data files which are residing onto a different disk. Next, once this child query is solved, the parent query, the main query it will definitely query the user's table space because the employee table resides on the user's table space. Now this becomes an overhead when your join is pretty big and you have multiple physical locations to query the data from. Now how would clusters help Oracle or the join queries to improve the performance? When it comes to table clusters, what Oracle did is it created a one big cluster, or you can create a one big cluster inside a database, and this cluster will hold all the tables which are frequently joined. I can have a big cluster. Let's take employee department cluster. This is a big cluster, and inside the cluster I have both the employee table and the department table. What Oracle will do is whenever the query is coming, remember it needs to get the data or get the output of the query from one cluster which already has both the rows from the employee table and it has rows from the department table, and both the tables will be joined based on the common column. The common column between the employee table and the department table would be department number. Best part is your employee cluster, when you create the entire cluster, you need to define a cluster key. Cluster key is nothing but the column which will be used to join all the tables inside the cluster. In our case, the cluster key would be department number. So next time when any query is coming inside the cluster which is trying to join both the employee table and the department table, what it will do is it will pick up the department number. It becomes more easy because everything is stored into one place. So the department number will be queried on the department table to get the output of our child query which said like get the department number where location is equal to LOC. we'll get the department number as 10, and also we'll get the employee details directly because employee table is also residing in the same cluster, and we'll have the output as whatever the employees who are residing in the 10 location or the department number 10. Now that is how the clusters will work inside the database. This is a eagle eye view regarding the clusters. Let us get more into details about the database clusters. So a cluster is one big table containing multiple small tables. You can create a cluster and you can put all the tables inside the cluster which share one single column. Remember, there should be one single column which is like a primary key or a foreign key among all those tables. You cannot put tables which do not share a single common column or which you consider it as a cluster key. We'll understand about cluster key in some time. Each table inside cluster have common columns. As I just now told you, each table inside cluster will have common column. That can be one single column, or there can be multiple columns which are considered as primary key or a foreign key. Because our table is small, or we have an employee and department table, we have only one common column, that is department number. But in real time, you can have something called as composite keys. What is a composite key? I'll take some time to explain you the composite key. For example, in the employee table, you create the primary key on employee number. But your department number, which is employed or department number column, this is a primary key of another table. And department or department number, the department number column, DEPT, department number column of the department table is primary key of department table. Remember, the department number which is inside the department table is the primary key of the department table. But the same column, when it is put inside the employee table, it becomes a foreign key. That means it's referring to a primary key of another table. That is how the primary key and foreign key relationship will work. But as I told you, these are small tables and we have only one primary key, one single foreign key. But sometimes inside a table, you can have composite keys. What do you mean by composite keys? It means a key column can have, when it has more than one column, it is called as composite key. Which means, let's take if we change primary key to employee number and the department number. Just an example. So when we create a primary key over employee number and department number, now this is called as a composite key. Composite key means having more than one column inside the key column. That's why each table inside cluster have common column or columns depending on the composite key. So because in real time you have big tables and big tables will have multiple keys, and in those keys they can be single key or composite key. Next, the common columns or column is called a cluster key. Depending on the key or the primary key or the foreign key, those will become the cluster key. So in general, the column on which all the tables are joined are nothing but called as cluster key. Cluster key must be specified during cluster table creations. When you create the cluster, you need to specify the key column over there. Otherwise, when you try to add the tables, if you do not specify the key column matching to the cluster key, it won't take the table over there. So when you create the cluster itself, you need to specify the key column. Now clustering of tables should be done when they are primarily queried, not modified. Remember, you should only cluster the tables when you know that a query will come to only select the data and not modify the table, because it becomes very tedious inside the clustering, or it will impact the performance when you try to modify the data inside a cluster. It's very easy to just query the data out of cluster. So it is not suggested to create clusters when you have more number of alters or updates or deletes. You can have a cluster when you have a lot of select statements and all the selects are having a lot of joins on two common tables. That time it's advisable to go for a cluster. Now when we have a table cluster, it will definitely reduce the disk IO, and that's when your database performance will increase. And also access time improves for joining of cluster tables. When you try to join the tables inside the cluster, the access time will increase because everything resides into one big cluster or at one place. So that's about overview of clusters. We'll get more inside the queries and all in some time. Creating cluster tables. Now there are some sample queries. Of course, these are not the real queries that we'll be using. We have an assignment for this activity which you will use to execute every step. Now creating a cluster. So create cluster statement will be used to create a big cluster. Now as I told you, you will have a cluster name, that is employee department cluster. This is the name of the big cluster. And in this one we have the key column, that is department ID. Will issue the data type of this column and size. Of course this size is not required because this is the size of your cluster. We are saying that 512 bytes should be the size of the cluster and limited to that side. But if you do so, your cluster cannot grow in case if new rows are coming in. So make sure you don't have that one in the create cluster statement. Next, a cluster cannot work well without an index. So you need to create an index on the cluster. So give the name to your index on the cluster. So just once you create the index, remember it will auto create on the key column, that is department ID. You don't need to specify on which column it should create the index. Oracle is smart, and because you have already specified the cluster key column, that is department ID, Oracle will automatically create this index, the one which you have mentioned, on the key column. Next, you create the tables inside the cluster. This is a logical cluster. Now when you add tables to the cluster, this becomes physical. Now create table employees. Let's take, you have the column names of the employees, and then you specify the cluster in which you want to create this table. So you are creating a table inside this cluster where you specify the key column. In our case, the key column would be department number. Next, you create the second table, the join table, because minimum two tables inside a cluster makes sense, because what clusters will solve the purpose is it will give faster access to the tables which are joined frequently. Next, we create the second table, that's department table. Inside the same cluster, you specify the cluster name, and the key column on which you want to make sure that key column is same as the cluster key column. In our case, it will all be department number because employee and department tables are joined on the key column, that's department number. That's about creating cluster tables. Let us look at the activity more in detail. So I'll pull up the tables and table cluster assignment. Now let us look at this assignment. But to get inside this assignment, what I'll do is I'll create a user, a new user. So create user cluster underscore test identified by, I'll just give the password as test. Now grant connect comma resource to cluster underscore test, and also will grant create session to cluster underscore test. Sorry, grant create session to cluster underscore test. Perfect. Now also because we'll be having the employee and department table, which are exactly same as Scott user tables, we need to grant the permissions to select the data from the employee and the department table of Scott schema to cluster test, because we'll be creating as those tables. We won't recreate the table and insert the data. So we'll create some tables referring to Scott.employee and Scott.department table, and then we'll play around with the cluster. So what we'll do is grant select on Scott.emp comma Scott.department to cluster underscore test. Sorry, grant select on Scott.emp to cluster underscore test, and grant select on Scott.department to cluster underscore test. Perfect. Now let us try to connect as cluster test user. So connect cluster underscore test slash the password is test, enter, connected. Now that we have given the select permissions on Scott.emp to cluster test, let us try to check if really we are able to select the data from Scott.emp. So select star from Scott.emp. We are able to see the data. Similarly, select star from Scott.department table. We are able to see the data. Good. Let us get inside our activity. First of all, we'll create a cluster table. So we'll create a big cluster, create cluster employees department cluster, and we are giving a key column as department ID. See, in both the tables, our employee table and department table, the key column is department number. But at cluster level, you can have a different name to your key column. We are giving department underscore ID as the name of your cluster key column. But inside this department ID, your department number is the one which will act as your cluster key for both the tables. So what you can do is, it's better to have the same name, but in case if you want to choose to have a different name, you can have it. So cluster key column can have a different name than the key column inside your tables. So just to show as an example, I have kept this name as different. So we'll proceed with the activity directly. In case if you want, you can keep the same name as your key columns. So we'll first create the cluster. So create cluster employee department cluster, department underscore ID number 2. So we are creating the cluster. It says the cluster has been created. Next is you need to create an index on the cluster table or entire cluster. Without creating an index on cluster table, you cannot proceed. This is an index cluster. We also have different types of clusters, but remember, index clusters are the ones which are frequently used, and that's why I haven't got into the other types of clusters. We also have hash clusters. Now that is something not used generally. These are the ones which are used most common. What you need to do is you need to create an index, and we are giving our own name to the index to cluster, and on this cluster it will create the index. Right. So index has been created. Now the question is, how do we check if the index has really been created? Describe user underscore indexes. Okay. Set line size 200. Describe user underscore indexes. So select index name table underscore name from user underscore indexes. We see that one index has been created on this employee department cluster. Remember, as I told you, a cluster is a big table. That's why it's showing up under table name. Okay. Next, we need to create tables inside cluster based on cluster key column. What we are doing is we are creating a table called as employee cluster under the cluster employee department cluster, where the key column is department number, as we are selecting the data from scott.emp, because we already have the select permissions, right? So we are creating a table inside the cluster employee department cluster by selecting entire rows from the scott.employee table. A table has been created. Next, same thing, we'll create the department table from the scott.department inside the cluster, the same cluster name we are giving. Do you see? It's the same cluster name, employee department cluster. So this cluster we just now created, right? Now what you can do is you can query the data normally from these cluster tables. How can we do that? So select star from EMP cluster. This is a table, right? Now we can see that the same data is coming up, which is exactly the same as select star from scott.emp. Same way, if you want to query the department table, so select star from department underscore cluster. So this is the table inside the same cluster. Now these two tables are inside one cluster. How does it help when you join? What will happen when you try to join these two tables? Because they are residing in the same cluster, the response time will be very fast. Let's take you perform select star from employee table emp underscore cluster, where department number is equal to select department number from department underscore cluster, where LOC is equal to let's take Chicago, CHICAGO. Oh, I missed the closing bracket. We have the output. When it comes to very big tables, of course, we cannot judge the performance right now in the cluster. When it comes to very big tables, and if you have clusters created, then the response time can definitely be judged on separately stored tables and a cluster table. This is a basic way in playing around with the cluster. A knowledge of clusters is important because in a reporting database where there are a lot of selects and all, if you see that there is a performance hit and there is a query which is always trying to join two tables, you can definitely create the clusters. Also, you can drop a single table inside the cluster by just issuing the drop table command. It will drop the table. There is no dependency on both the tables that you need to drop other table before dropping the first table or the second table. You can drop the tables independently because you create the tables independently, right? In this statement, we have created the tables independently, and that's why we are able to drop the tables independently. And finally, you can drop the entire cluster also. Remember, there's no prerequisite saying like you need to drop the tables before dropping the cluster. You can drop the entire cluster as well at one shot. These are the few commands which will help you play around with the clusters. And the final slide, how cluster table looks like. So what happens inside the cluster? See, when you have two tables stored separately, even though you have a department ID column which is joining both the tables, so the physical storage will store both the tables separately, and when you query any table or any join query, it will get the data out of those two physical locations where the tables are stored. But when it comes to the cluster, what happens inside a cluster is you have the key column and the rows are stored from both the tables. For example, let's take this is an employee and department table. Both are joined with the department ID. The department ID 20 is mapped to department name marketing, and for this 20 department ID, there are only two employee IDs which are mapped. That is 201 and 202. Next is we have the department ID 110. for which we have the name is accounting, and accounting department is having only two people who are mapped, that is 205 and 206. When it comes to an cluster table, the key column will be mentioned first, that is 20, and this key column will contain the rows which are mapped to this department in one single area. For example, this is 20, and for 20 we have the department name, that is marketing, location ID is 1800. That means the complete row from the department table, and also it will store all the rows from the employee table. So employee ID 201, 202, the last name and other columns from the employee table is assigned to this key column. Now that's why it becomes easy when we query where department ID is equal to 20. Now the records from department table and employee table are stored at one location. The retrieval or the access time will be very fast. Same thing goes with the 110 department ID. You have the accounting department and location ID, and you also have all the employees which belongs to the 110 department. And that's how, rather than physically getting the data from two different tables, everything is now stored in one big table at OS level, that is cluster, and everything is at one place. So with each department or the key column, you have the records from both the tables. So it becomes easy to pull out the data at one shot when you refer to the key columns. Now that is the way clusters work inside a database.